Welcome to chapter 25, part 6. This is tubular secretion. This is what happens to the tube fluid as we add substances to the pre-urine or tube fluid that were not previously filtered. This is probably the very shortest lecture we'll have in this chapter. So here we are. This is step 3. Remember, we had glomerular filtration, tubular reabsorption, and this is part 3, tubular secretion. So tubular secretion is where we move substances from the blood into the tubule. So it's opposite of tubular secretion. And this is important because we need to get rid of some of these drugs or metabolites that were either too big to cross through the glomerular filtration membrane, because remember that was that like coffee filter colander, and the big stuff it can't go through. So some of these metabolites are really big and we need to get rid of them. So we're going to secrete them in a different place, not through that glomerular membrane. We're also going to use tubular secretion to eliminate some undesirable substances that were passively reabsorbed. Remember, we had urea being reabsorbed in the proximal convoluted tubules. We also need to get rid of extra potassium. K+ is potassium. That was that aldosterone effect. And we are going to need to alter either secreting hydrogen ion. That's H+ is hydrogen ion, the most acidic substance we've got, or bicarbonate, which is the base. So we use those two to control blood pH. If blood pH is too acidic, that means the pH is too low, we are going to secrete some hydrogen ion into the urine, making the urine more acidic and making the blood less acidic. The opposite happens if the blood becomes too basic. We can then secrete hydrogen ion into the collecting duct and lower the blood pH. All right, so we said this before, tubular secretion is when solutes move from the blood in the peritubular capillaries through the interstitial fluids. Remember, there's a little bit of fluid between where the blood is and where the tube is. And we're going to move it from the blood into the tube. In the proximal convoluted tubule, we'll see potassium moving as part of the aldosterone effect, where there's an exchange of sodium when blood pressure is low. We're also going to see ammonia, which is part of the nitrogen deamination product. Creatinine, same thing as a part of protein breakdown, and some organic acids, drugs, toxins, and urea. Also, and then we're going to see the body pH is too acidic. We secrete hydrogen ion in exchange for sodium when pH is, oops, hold on, I messed that up. Let me fix this. Okay, so I fixed that. So when the pH is too acidic, the pH is too low, we secrete the acid, hydrogen ion. When body pH is too basic or alkaline, we secrete bicarbonate to lower the pH of the body. In the next chapter, we'll look at acid-base balance in more depth. Urea is secreted into the ascending loop via diffusion and then reabsorbed out of the collecting duct into the interstitial. So this is a cycle of recycling. We use urea. We know we have to get rid of it, right? Because it's a waste product of protein metabolism. But because it is so common, we have a lot of it, we use it to maintain a concentration gradient in the fluid in the medulla, so the surrounding of the nephron and loop. And we're going to recycle it from the collecting duct to the ascending loop. And because of those different permeabilities in the loop, we're going to notice and create a much higher concentration of urea in the bottom of the loop and a lower in the top. And we're going to use that concentration gradient to draw water out of the conducting duct in the presence of ADH. So remember, ADH is going to tell us to concentrate urine. It's going to open those doors, the aquaporins. And then if we have a super high concentration of urea, those aquaporins, the water will move out and try to dilute that. So it's going to be moving out of the collecting duct and therefore concentrating urine. And we use ADH to enhance this urea recycling to increase this gradient. So this gradient always has to be available so that we can concentrate more urine and then concentrate it more and concentrate it more. So this is one of the rare examples of a positive feedback loop. Remember, in the past, we have talked about childbirth and blood clotting, lactation being examples of positive feedback loop. Here is another one. This is how we concentrate urine. So the more we need to concentrate urine, the more we're going to concentrate urea. And then urea will draw more water out, which concentrates more. And it's this nice, beautiful cycle. And again, you might be saying, what in the world? Who cares? Why is this so important? But remember, concentrating urine is a life-saving process. All right, here is a summary of what is going on. So the reabsorption is in the blue. So we learned that in the proximal convoluted tubule, we have reabsorption of all the nutrients, right? Or it's like 99%, glucose, amino acids, proteins, vitamins. We do see some reabsorption of urea, which we're eventually going to need to get rid of, and a lot of electrolytes. I'm just kind of grouping sodium, potassium, calcium, magnesium, chloride, and all of that into kind of a group of electrolytes right now. When I specify something about sodium or potassium, then you need to know that, but otherwise they're kind of grouped together. And I did not go through every single one of these because I didn't want to make your head spin. We also see a lot of water. So remember, the water follows the sodium, so we got about 65%. We also hear the pink is a secretion. So even though urea is actively reabsorbed, we are going to secrete it because we got to get rid of it. And also this uric acid, creatinine, hydrogen ion here, some ammonia, and some drugs. So these are things that were either too big or didn't get filtered out of the glomerulus here. We're going to just put them back in here. Here is your descending limb of the nephron, where only water can go out, but urea can go in. Solutes cannot come out, only water comes out. As we go up, we're going to see water can't move, but these electrolytes can move out. In the distal convoluted tubule, we're going to see the fine-tuning of what the body needs to reabsorb to keep it alive and what it needs to secrete to keep it alive. So you're going to see hydrogen ion, potassium, or ammonia, depending on what the body needs. It's not all the time. And also sodium chloride and water here. And then as we go down the collecting duct, we're going to see the movement out of both water and urea, because the urea goes out and the water follows it, because especially the deeper we get in here, remember, we're going to, well, we haven't seen this yet, but we're going to see a high concentration of urea here and a low here, and that high concentration is going to suck this water out. Just imagine urea being salt. Okay, so it's a super concentrated solution that needs to be diluted, and we're going to suck the water out, and that makes your urine more and more dark in a smaller volume.